Hi everybody, welcome back to my YouTube channel on theoretical physics with Mark Weitzman. I'd like to begin today with a video from my QFT review blog. So this is going to be 3 videos. It's going to be 8A, 8B, 8C, QFT review blog video. And today we're mostly focusing on a discussion that Z has in his QFT nutshell book, textbook. Very early on, he gives a discussion of repulsion, and attraction in Scalar, vector, and tensor theories. So basically, we're trying to show how QFT sort of explains why scalar particles are attractive, why like particles in a vector theory like electromagnetism repel each other, and like particles in a tensor theory like gravity attract each other. So it's a very interesting argument, and Z uses very early on the path integral formalism. At least he starts out with that. He also does canonical quantization, but he starts out with path integral. And, I'll outline this formalism. I'm not going to derive it. I'll just outline, I'll sketch the formalism. And we'll try and see what's the difference between the spin 0, spin 1 half, not spin 1 half, spin 0, spin 1, and spin 2 theories. So let's start with the basic path integral. Basic path integral equation. Now this is derived in many places. Not just in quantum field theory books like Shankar's book. QM book derives this. And so we define a matrix element between the position coordinate of a final state, e to the minus I times the Hamiltonian times a long time period t, qi. This is equal to the integral of d qt e to the I, the integral from 0 to t. Sometimes you just see it from minus infinity to infinity of the Lagrangian. Now, this formula isn't always valid. There are some, this holds for the basic Lagrangians, which is like p squared over 2m plus a potential. You get different things. You really should go through the Hamiltonian version of this in books like certain advanced quantum field theory books. I can't remember his name right now. They discuss going through the Hamiltonian and ending up at the Lagrangian, but we're not interested in such technicalities here. And something like dq. I don't know why it doesn't erase that. Something like dq of t is a measure, and it's ill-defined, unless you go maybe into Euclidean space. But we're not going to worry about all these formal things. Now, in these basic formulas, this is the QM formula. We're going to generalize to QFT, and we will add sources and sink. Schwinger used to describe quantum field theory as sorcery, and he wrote like several books. He tried to develop the whole theory based on sources and sinks. So now we'll end up getting what we call the basic object in the path integral field theory. It's usually almost always called Z, and it's going to be the integral. And now in a field theory, our positions are parameters, and our basic dynamical variables are the fields at each position. And we're going to have e to the I, and now we're going to integrate over all of space-time. And we're going to have something like a typical Lagrangian for a scalar field. I'm doing the scalar field here, minus the potential of a scalar field, plus, and here's where we add in the sources, j of x times phi of x. So we're coupling a source, j, to a field. And now, these path integrals can't really be involved except for the free field theory. So we're going to use the free field Lagrangian. This leads to the Klein-Gordon equation. And now we're going to get Gaussian or quadratic integrals, and these we can evaluate, at least formally. And so we're going to get something like, let me put a star next to this one. That's one of our equations, and now we're going to get another equation. Set of equations. Z is equal to the integral of d phi e to the I, the integral of d4x. If we integrate by parts here, we can put it more in like a matrix type of form. Minus 1/2 phi partial squared plus m squared phi. So now you can see this is like a matrix. And this formula is well known, plus j of x, phi of x. And this ends up, when you use your basic formulas for Gaussian integrals, you're going to get c e to the minus I over 2 double integral d4x d4y jx dx minus y jy, and this is going to be defined to be c e to the I w of j. Now I said most quantum field theory books, I believe, use z and w. So one or two of them actually reverse this. You call this w and call this z, but you'll see that right away. And this object is, of course, our propagator, and it satisfies minus the partial squared plus m squared. It's essentially the inverse of this operator. D x minus y equals del 4 x minus y. And using this equation for the propagator, and we'll also make a substitution of m squared goes to m squared minus I epsilon, which helps with convergence issues. we'll get some kind of factor like e to the minus epsilon, the integral of d4x phi squared, which is good. And it defines poles as well. So using this, we're going to get dx minus y is equal to the integral of d4k over 2 pi to the 4th e to the ik x minus y k squared minus m squared plus I epsilon. And if you've done canonical quantization, you've seen this before. Now, remembering that z of j is equal to e to the I w of j, and using the equations star star, as well as the Fourier transform of the source, I'm sorry, this is k, j of k is defined to be the integral of d4x e to the minus ikx j of x. This leads to w of j is minus 1/2 the integral of d4k 2 pi to the 4th jk these asterisks here, for usually the sources are real, so these might not even come into play. jk. And this is sort of our key equation that we're going to use over and over again. This is the scalar version. Scalar version. For w of j. Now, you might say, well, how does this relate? How does this relate to particles attracting each other? So what we do is we treat a specific source. There's no difference between sources and sinks in the scalar thing, or a little difference. So let's imagine we have a particle at x1 and we have a particle at x2. And let's neglect, because we're not professional field theorists yet, self-interacting terms. W. So putting this in here, after we take the Fourier transform, we get Wj is equal to the integral dx0. And this is just going to be our time. And we get the integral of d3k 2 pi cubed e to the I k dot x1 minus x2. These are all vectors here. then divided by k squared plus, I have to check that, see if that's right there. Okay, yeah, this is the vector now. K squared plus m squared. Okay. Now, so this is a lot of progress. Remember that z is equal to basically 0 e to the minus I h t 0. And so it has time dependence. E to the minus I e t. And since we had the equation before where we set it equal to e to the I w j, this implies that I w equals minus I e t. Not worrying about some constants that we'll get rid of anyway on normalization. So this gives the expression for the energy. E equal minus the integral d3k 2 pi cubed e to the I k dot k squared plus m squared. Now, we've done this integral before, and I'm not going to do it again. It is easily evaluated by using spherical coordinates. And orienting the K3 axis along x1 minus x2. So if you do that, some routine integrals, we've done this before. I've done it before in some of my videos. And you'll end up getting E equals minus 1 over 4 pi r e to the minus mr. R is equal to the absolute value of x1 minus x2. So so this is good. This is good. Good. We get an attractive force. Okay. Also, in the massless limit, we get the usual inverse square force. For massive, we have the Yukawa force for mesons. So this completes the spin zero case, spin zero scalar case. Okay, comma, and in the next video, we will go to the spin one vector electromagnetism case. Okay, so I'll see you next time, next video. And all 3 videos should be available at the same time. The second video will be on electromagnetism. The third video will be on gravity. Thank you for watching.